Alrighty, Stokes' law, right? Okay, so we've got this particle that's falling at its terminal velocity. So let's draw a little picture of that. Okay, when it falls at terminal velocity, that means that the drag force, the Stokes force, right, equals the weight of the object, right? These guys are equal but opposite. This is our m times g, right? Ultimately, m times g is going to be rho times v times g, which ultimately becomes rho times 4/3 pi r to the third g, right? Okay. Now the only variation really, this one is through air, so we're going to neglect the buoyant force. The only variation is that sometimes, see with air, there's like a tiny buoyant force, right? If it's falling through water, though, the buoyant force could be, in this case, it could be like 1/3 of the, or it could be all of it, right? Water can't fall through water. Okay. Anyway, but there could be a buoyant force, right? So sometimes we use the buoyant force is actually acting up, and it's significant. Okay. In this case, it's just the Stokes force and the force of gravity, right? And we just set those equal. So the Stokes force is 6 pi eta. Is it r and then v? I think that's all it is, right? And then we just set that equal to the density times the volume. Right? What's its radius? Oh, hey, that's going to be tough. Okay, and then times g, right? Okay, so now we're all set. Notice that pi cancels. That's fun. Notice that one of the r's cancels. Right? Okay, so let's see. So now we've got 6 4 rho r squared g over 3. Is that it? Yeah, that is it. All right, so let's see. So I guess what we're going to do is we're going to multiply, cross multiply. So we'll get 18/4 or 9 halves, right? Okay, let's see. This guy will still be in the numerator. This guy will be there. Rho and g will be on the bottom. And then that equals r squared, right? So then we're going to square root this guy, right? All right, there we go. Okay, so it's the square root of 9 times the viscosity, 1.81. Is that right? Yeah. Times the velocity, which is 0.00315, divided by 2 times the density of the drop, times 9.81. Okay, now so sad I don't have my calculator. They can make it actually look like that. Okay, I'm going to go square root, left parenthesis, 9 times 1.81, e minus 5 times 0.00315, divided by, and then parenthesis, I have to do my whole denominator, 2 times 1,000 times 9.81, right parenthesis, right parenthesis. Boom, I get 5.11 times 10 to the minus 6th meters, right? All right. Now, that's all well and fine. Let me show you what you have to do if it's falling through something where the buoyancy is significant, okay? If the buoyancy is significant, then we've got to add another term on this side. So let me just show you that. Okay, I'm going to erase. Are you ready? 3, 2, 1. Boom, it's gone. Okay, so now we've got object falling through the air, right? We've got the Stokes force, and then we also have a buoyant force, right? And the Stokes force, and those together equal mg, right? So we go 6 pi eta, I think is what it is, right? RV, okay, plus the buoyant force, which is the density of the fluid, right, times the volume of the, right, times g, right? It's the weight of the air displaced in this case, and that's not much. That's why we ignored it in the previous part, right? That equals the density of the object, right? We're just making the mass, right? This becomes density times volume times g, right? volume of the object, right, times G, okay? Now, before you get all, freaked out about this, right, do you see what's going to happen here? Really what we can do is we can just write it this way, 6 pi r v, this is velocity, don't confuse it with volume, right, is equal to, parenthesis, rho of the object minus rho of the fluid, volume G. All the buoyant force does is it just adds that. You subtract the density of the fluid. Then you're all set. Okay? So again, this is going to become rho of the object minus rho of the fluid, right? Times 4/3 pi r to the third times G, right? And then we're going to do the same thing. Pi goes away. R, we can get rid of one of the r's. Right? And we'll end up with, when we solve it, right, we'll end up with the radius being the square root of, what is it? It's 9/2, right? And in the numerator, it's this guy and this guy, right? And then in this case, in the denominator, instead of just being one rho, it'll be this factor right here. Rho of the object minus rho of the fluid times G. I'm skipping mathematical steps here. There's like cross multiplying, and we combined the 3 and the 6 and 18 and the 4, and the 18/4 is 9/2 and all this stuff, right? Okay, so that's going to be the square root of 9 times 1.81 times 0.00315 divided by 2 times 1,000 minus 1.29, right? So that's the density of air. Okay, I didn't even give it to you, so you couldn't even. 9.81. Now notice that that's 1 part in 1,000, right? That's going to have a tiny effect. I'm just going to go second entry on my calculator. I'm going to go insert a parenthesis there. Insert minus 1.29, right parenthesis. Boom. And now I get 5.117. It actually rounds up to 5.12, which is, about 1 part in 1,000, although it's a square root, so it's not, it's actually not as big as that, right? Okay, so this is why we can ignore the buoyancy of air, but some of the problems, I think a couple of the assessments have it falling through a fluid, so just remember the trick. I mean, this is how you set it up, but ultimately you just end up setting it up and you just say like the equivalent weight or mass is density minus density. Time's up.